Good afternoon, everyone. Is
Yeah,
my voice very audible?
it is very audible, Godfrey. I can hear you clearly.
Okay.
I can hear you.
So you're all welcome to the training section for the transmission architecture.
Thank you, Mr. Godfrey.
Okay. So let me give a brief introduction about myself. My name is Godfrey Ajaku. I have about 12 years experience in the telecom industry. I started my work as national service personnel with Volta River Authority, where I worked at the radio and fiber network department. And, I had the opportunity to study all their networks and then also help with the major fiber rollout during my time there. Then after my service, I moved to join the first government-owned fiber network in the country, the National Communication Backbone Company, popularly known as the NCBC. There, I was part of the team that rolled out the Kumasi to Tamale fiber transmission stretch. Right after that, I joined MTN to roll out their transmission network from Accra to Kumasi, precisely the fiber rollout. Then I joined Tigo when they were ready to roll out the Golden Triangle, as it's popularly known, the fiber between Accra, Kumasi, Takoradi, and back to Accra. Since then, I've been working on the maintenance of the transmission networks for Airtel Tigo, both microwave and fiber. So that's a bit of my background. So as mentioned earlier, we are going to talk about transmission architecture. For this particular subject, we'll be talking about, we'll be doing an introduction to the transmission network. Can everybody see my screen?
Yes, please.
Okay. So, about
Yeah. Yes, please. Yes.
okay. So
Godfrey,
yeah,
can you go to presentation mode? Can you click so that we can see the? It's at the left hand corner. You see presentation mode down there. Okay, I've requested control. You can give it to me. You can give me control. Just give me control from your side.
okay. Maybe it's yet to come. I've not seen any request.
Okay.
Okay, let me stop sharing and then you can request for the control again.
Okay, let me. Godfrey,
Hello.
I'm still not. Let me. Unless you share it, just share your screen again. It looks like you've
Okay.
kindly share your screen again.
Okay, I'm
Yeah.
sharing. No, not this one. Hold on.
You see at the top of your, go to slideshow and then click from current slide. Just at the top tabs, you see slideshow at the presentation.
Slideshow.
Yes. On the presentation, you will see slideshow.
I'm looking for. I have just some. Hold on. I don't see that function.
Okay.
I only have show device settings, show meeting details, enter full screen.
No. This one is on the presentation, the slide presentation itself, not on the meeting.
Oh, okay. You mean the PowerPoint?
Yeah. In the PowerPoint, yes.
Okay, no problem. Let me
Yeah.
see. Okay.
So you see slideshow, then you click on from current slide. See slideshow. After animation slideshow.
Mine is at the bottom. I need to hide some buttons before.
Okay. All right. We're good. We're good now.
All right. So when we talk of transmission, in general, it's the term used to describe the process where traffic, in this case, voice, data, video, etc., is sent and propagated over a medium from the source to and we are interested in the medium. We are much interested in this topic about the medium in which the data is translated. There is so much noise at the back. Can somebody mute? Hello?
Yeah, hello, Godfrey.
There's some noise at the background.
Yeah, someone is unmuted himself.
Okay, that's fine. So we are interested about the medium in which the signal is transmitted from the source to the destination. We have two major types in this particular instance. We have the guided media and then the unguided media. By guided media, we mean wired media. Wired media, we have a lot of types. We have the copper, we have coaxial cables, we have fiber cables. Each of these wired or guided media has its own advantages and disadvantages. Then we have the unguided media, which we talk about the microwave and then VSAT. We also have a transmission over a vacuum or water. These are wireless and guided media. They are all used to transmit information from source to sink. Like I mentioned, each of these has its own advantages and disadvantages. The successful transmission of data depends on two basic factors. Of these factors, the most important is the characteristic of the transmission medium. Then the quality of the signal being transmitted. These are the two major guidelines in transmission. If we are talking about the characteristics of the transmission media, we can talk about each transmission media and its characteristics. In fact, in planning a transmission network, this is the first thing that comes to mind when you want to know or you want to plan a transmission network. Go backward. Good. So when we take, for instance, the guided media, when you take a twisted pair, for instance, twisted pair can only transmit capacities up, and some few instances we have experimental tests of up to 10 gig on some few occasions, but the standard transmission capacity for a twisted pair generally is up to speeds of 1 gig. When you take coaxial cables can take data rates of up to 80 times the capacity of a twisted pair cable. Then when you move to fiber cable, you have data rates of up to 26,000 times the capacity of a twisted pair. By now, you see why everybody is rushing into fiber transmission, because of the unlimited, so to say, capacity it can transmit. Now, let's see some examples of these guided wired media. We talk of twisted pair. We have the LAN cables we use most of the time to connect to our LAN ports. They are examples of twisted pair cables. When you want to talk about coaxial cables, a very good example is the cable we use to connect from our antenna to our TV sets in our rooms. That cable is a coaxial cable. Fiber cables are not usually seen in our homes, though we have devices that can take fiber cables as their interface. Sorry. We normally find these optical fiber cables in the telecom industry, where high bit data rates are involved. Now, when you come to wireless media, where we have the microwaves and the satellites, they can do data rates of up to, we have E-band that can do up to 10 gig over short distances. Generally, their data rates are in the region of 1 gigs and a little over 1 gigs. We have Aviat that can do up to 2.5 gig data rates. These have the distance limitation. The more you go, the more your dispersion and the less signal quality you incur. So when you are planning a transmission network, for instance, the characteristics of your medium available should define or play a major role in what you purchase as your transmission media. The capacity you want to transmit from source to sink is largely determined by your media. Now, let's talk about the advantages of the two main transmission media we have in the telecom industry, the microwave and the fiber. Like I mentioned, they all have their advantages and disadvantages. Putting the data rates aside, the cost of deployment is also a major factor when it comes to transmission network deployment or planning. Microwaves generally have less cost of deployment and means that you can deploy it over a short time compared to the fiber. You have a lower startup and operational cost. Now, you will not need to encounter any right-of-way issues. What we mean by ROW is a right-of-way issues. We will talk more about that when we are discussing the fiber part. Now you have a low MTTR as well. MTTR means the mean time to restore in the event of a failure. So what it means is that because microwaves are normally point-to-point, you only have 2 points to visit to address a fault: the source device and the sink device. These are the portions of the network which can fail. So when there's an outage, you can only look at these 2 sections and you will find the solution to the failure. Let's relate these advantages to the fiber. The first one we will talk about is the operational cost. The operational cost of rolling out fiber is extremely expensive. It means largely acquiring the fiber path. Assuming you are covering a distance from point A to point B of, say, 50 kilometers. That means that each of the path of these 50 kilometers has to be assessed either by your method of, largely by your method of deployment, if you are going aerial or underground. If you are going underground, for instance, each of these 50-kilometer stretch needs to be opened, cables laid, buried, and backfilled. That means that you need 50 kilometers of fiber cable to be able to run your transmission media from point A to point B. Unlike a microwave section, which will only require 2 microwave radios from point A to point B. This means the operational costs of rolling out a fiber network is way more expensive compared to rolling out a microwave network. The same applies to rolling out a copper or coaxial cable network. Now, the other part of it, which is a major headache in rolling out a guided media, are right-of-way issues. Right-of-way issues is a major challenge, especially in Ghana, where right-of-ways are not defined. Right-of-way basically means the path defined by the authorities for any operator to place his cable. The path defined by the authorities for any operator to pass his cable. That is what is called the right of way, or ROW. As you know, not each of these paths is owned by the government. So most of the time in deploying such fiber networks or cable network, you need to seek permission from the government and also seek permission from each person who owns a section of the fiber or cable path. The permission has to be granted before you can safely pass the cable. This normally increases the deployment time of cable fiber or cable rollouts compared to microwave rollouts. It also increases the cost. For instance, the government requires that you pay a fee for each kilometer you pass a fiber or a cable. The owner of the land also requires that a fee is paid if the government doesn't regulate that section. So in terms of cost, all these things are factors that raise the operational costs or the implementation costs of a guided media. Now, if you talk of the MTTR, let's use the same example, the rollout of a 50-kilometer section. Each of these 50-kilometer section is a possible point of failure. So assuming there is a break, unlike a microwave section where you can only go to point A or point B and see or troubleshoot a fault, for a cabled or a guided media, each section of the path is important. Each section of the path is a possible point of failure. So 50 kilometers of guided media is a possible point of failure. And so you need to trace the path to identify whether there is a break on this 50-kilometer stretch. You can imagine the works involved. You need to drive along the whole path to inspect physically whether that is ongoing on the stretch that has damaged the media that requires repair. In terms of a copper or coaxial cable, this has to be done manually by physical inspection. If you are using a fiber cable, there is a tool that is normally used to measure the fault point or the break by going to point A or point B or your source or sink to run a trace. The trace will identify the fault point in distance. So then an engineer drives along the route measuring the distance of the fault point to identify the break points and then restore the service. This normally increases the time to restore a failure. The media is a guided media, unlike microwave. Most of the time, the advantages of the guided media far outweighs the disadvantages. So though the MTTR is normally longer, because of the advantages the guided media gives compared to the unguided media, operators still go in for it. For instance, if you are talking about the capacity constraints microwave links give, assuming you want to transmit data rates in the gigabit, 10 gigabits and 100 gigabits, there is no microwave transmission media that currently can support that. So because of the advantages, operators normally will go for the guided media and manage the disadvantages that come with it. I have a table, a small table here that summarizes the advantages of the wireless or unguided media compared to the guided media. If you can see my screen, you have, for instance, wireless. The advantages is easy and inexpensive to deploy, as we mentioned earlier. It naturally supports mobility and naturally supports broadcast. Disadvantages of the wireless: transmission interference is very rampant in wireless transmission media. Now, strengths vary greatly. As I mentioned earlier, you are only limited to a few gigabits per kilometer. Unlike wired, for instance, fiber, you have the advantage of transmitting higher data rates from point to point. As we mentioned earlier, it comes to the disadvantage of the expensive nature of deployment, and it doesn't support mobility. I think I've mentioned all these in my earlier submission. Some of the manufacturers of fiber cables currently in the world, these are the top manufacturers of fiber cables in the world. We have Nokia, Siemens, OFS, Fiber Optic Systems, Musa Electronics, Roebuck Fluid Power Company, Fujikura, Corning, and YOFC. In Ghana, the supplier with a widely used footprint is the YOFC company. We have few OFS cables in the country. And we also have some Corning cables also in the country. If you talk about the microwave suppliers, we also have Nokia, we have Nera, we have NEC, we have Siemens, we have Digital Microwave Corporation, Fujitsu, we have Ericsson, we have Alcatel, Huawei, Harris. I think we all know of Ericsson and Huawei. I think they are the dominants in this industry in Africa. NEC is also widespread, and Nokia also widespread, with a lot of footprints in Africa. Now, when you have your media in place, you need to know how you intend to connect your nodes. Transmission media normally has the devices that does the signal processing and the media that carries the signal, as we mentioned earlier. We have four different architectures that links these nodes together. Each of these has its own advantage and disadvantages. We have the star connection. We have the ring connection. We have the mesh connection, and we have combinations of the above. We have combinations of the star, the ring, and then the mesh. Let's look at how the star architecture is like. The star architecture has a central node which has connections to other nodes in the network. If you see my screen, you see the node in the middle, which aggregates all the other nodes, for example, A, C, E, and D. B is the common point that connects all these connections together. Now, for an N stations, these nodes A, B, C, D are referred to as stations. For N stations, you have N minus 1 transmission links that will be required. Let's see if this formula works. Let's count the number of stations in this. We have A with 1, D which is 2, E which is 3, C which is 4, and B which is 5. So for 5 stations, how many links do we require to establish a star connection? We have N in this case is 5. If we apply our formula, 5 minus 1, giving us 4 transmission links required. Now let's count the number of links here. We have 1, 2, 3, 4, which gives the number of media required to establish connections in the star topology to 5 stations. It means that each station depends only on 1 link. The disadvantage of this star topology is that if the node B fails, all the other links in this architecture has failed or will also fail. Because A, for instance, has only 1 link to B, D has only 1 link to B, E has 1 link to B, and C has 1 link to B. The device B controls all the other 4 nodes. So when the equipment fails, the equipment at B or the station B fails, the whole network collapses and you have a big outage. There could be an instance where individual links will fail and it will affect only, or it will isolate only the station that has failed. For instance, if D fails, only the link to D is isolated. All other links will be online. Let's see the other architecture. This is called the SPUR architecture. In the SPUR architecture, you basically have a linear route where each link in the transmission point to point depends on each other, apart from the source. For instance, if you are transmitting from A to E, for instance, let's reverse it. E depends on D, C, B to reach A, if A is your controller node. D depends on C, B, A to reach A. The same way, C depends on B to reach A. The disadvantage of this is that, obviously, if the link between A to B fails, the network collapses because B, C, D, and E will be isolated. This is normally not an ideal network architecture, but depending on resource availability, an operator may go in for such network. To prevent, well, in the same way, the number of transmission links required to establish, for instance, 5 stations, the same formula applies. So for N stations, we have N minus 1 links that will be required. So in the same way, we have 5 stations as in A, B, C, D, and E. The number of media 1, 2, 3, 4, and it still obeys the rule. As I mentioned, this type of architecture is prone to network outages. This SPUR architecture is prone to a lot of outages. The main difference between this and the previous one is that the SPUR architecture, when an equipment fails, you lose the node. So an equipment failure can cause the whole network to collapse. The central controller equipment, or the central controller station, in this case, the station B, can fail and collapse the whole network. In this instance, the SPUR architecture, when the media between A and B fails, the whole network fails. In the same way, if the node A fails, the whole network also fails. That's the main difference between the two. Now, the problem created by the SPUR architecture is solved by the ring or loop architecture. In this instance, as you see, the network that starts from A, B, A, C, E, B, and D is closed by having a connection from the last point back to the source node. So this architecture forms a loop or a ring. The advantage this gives is that when there is a failure in any of the transmission routes, there is an alternative route available. For instance, if you're looking at point A to D, for instance, if you take off the media between and D, you can see that the services can be configured such that it will use D service can be configured such that it will use D, B, E, C, and back to A. That means that at any point when a single media fails, you don't have any network outage. This gives a very resilient network. In the other hand, when a station fails, for instance, if station B fails, the other stations are still available to carry traffic. And so you don't have a big outage as compared to the other types. What we realize is that in the ring architecture, for N stations, you need N links to establish the ring architecture. So most of the time, operators will opt for a ring topology. But I realize that this will put an extra, this requires an extra link to make it work. Because the node that opens the link should have a closure as well. So ideally, this